Click the bell icon to get latest videos from Ekeeda.
Hello friends, so in this particular video we are going to study the motion of an electron which is injected perpendicular to a uniform electric field. So the motion of an electron which is injected perpendicular to an electric field will actually have a velocity Vx0 in the x direction, and initially there will be no velocity in the y direction. Let us understand this with the help of a figure. Here is a figure. So we have the electric field that is established between these two plates that are separated by a distance L, and this plates is of length L, and here is the electron that is injected with a velocity v0 in the x direction. But the minute it is entering this particular field in the x direction, there is a force that is acting in the y direction. Remember, an electron is negatively charged, and therefore the force will not be in the direction of the electric field, but it will be in a direction opposite to that. Thus the electron will be deflected simultaneously, not only in the x direction due to its velocity in the x direction, but also it will be deflected in the y direction due to the force acting in the y direction, and this force is nothing but the electric force. Let us now write down an expression for this force. So the expression for the force is Fy is equal to minus of q into E. So this is going to be the force. So the acceleration because of this particular force in the y direction is going to be equal to Ay is going to be equal to QE upon m. The basic definition for the force, which is nothing but mass into acceleration. So here I have the acceleration in the y direction. Similarly, let us try to find out what is the velocity in the y direction. For finding out the velocity in the y direction, we will actually use the kinematic equation. And what is the kinematic equation that I will use? It is as simple as V is equal to U. The kinematical equation is V is equal to U plus AT. U is nothing but the initial velocity, A is nothing but the acceleration which you got over here, and T is nothing but the time. Therefore your V, which is the velocity in the y direction, will be equal to 0, because initially there was no velocity in the y direction, there was velocity only in the x direction. 0 plus the acceleration in the y direction, which is going to be equal to QEm, and this is multiplied by T. In order to find out the expression for T, we know that the velocity in the x direction is equal to Vx, and therefore the distance that is traversed by the electron due to its velocity in the x direction will actually be equal to Vx is equal to, the velocity will be equal to distance upon the time, and therefore your time factor will actually be equal to x upon Vx. So this gives me an expression for the time period. I can substitute this particular expression in this expression to find out the velocity in the y direction, which is equal to Vy is equal to QEm multiplied by T is equal to x upon Vx. Having found out the velocity, there is one more expression that we'll have to do. What is the distance that it has actually traversed? So in order to find out what is the distance that it has traversed, for that we use one more kinematic expression, that is S is equal to ut plus half of at square. So your S will actually be equal to, S in this case is your y, and your y will actually be equal to S is equal to ut, that is going to be 0 because your u, which is the initial velocity in the y direction, is 0, and plus half of at square, acceleration we have over here, which is going to be equal to qe upon m and into t. So this is the expression for the displacement, which I am simply encircling it. For the time, once again I can use the same expression over here, that is v upon vx, and therefore your y will be equal to half into qe upon m. We have the expression over here for the displacement, y is equal to half into qe upon m, and of course this is t square. So y is actually equal to half into qm into t square. From t there is nothing but x square upon your vx square. So one can see that if at all these quantities are constants out over here, I can say that y is equal to some quantity k into x square, and thus the equation is that of a parabola. So one can very well say from this expression that the motion of an electron which is injected with a velocity v0 in the x direction is described by a parabola y is equal to k into x square. So when the electron is appearing out from this electric field, it is having a velocity v0 in the x direction. Remember, this velocity v0 is unaltered, and it is going to have a velocity vy in the y direction, and this velocity is because of the electric field which has acted upon it for a distance L. This electron is now incident on a screen, and it will produce a displacement over here that is nothing but y. Now when it produces a displacement y, I need to find out in this case what is exactly this displacement which is there, that is y. And in order to find out this particular displacement, we proceed in the following manner. We begin with the expression which we have already had. Y is equal to half into q into e upon m into x square upon vx square. Or for that matter, this is going to be equal to y is equal to half into q into e upon m into your x is equal to L. Therefore, this is going to be equal to L square upon your vx square. This is once again an expression for the parabola. At the other end, from the figure, we have that the displacement y is equal to d into tan of theta, wherein d is the distance of the screen from the two plates where we are subjecting the electron to the electric field. So y is equal to d into tan theta, but your tan theta is actually equal to v, that is the vector in the y direction divided by the vector in the x direction, the velocity vector in the y direction and the velocity vector in the x direction. So your y once again is equal to d into vy upon vx. The expression for vy is, so the expression for your vy is ayt upon vx, wherein ay is the acceleration in the y direction because of the electric field, which works out to d into, the acceleration will be equal to e into e upon m into, now this will actually be equal to t upon v into x. By definition, the time period for which the electron is within the distance L will be given by the factor d into e upon m. So the time period will actually be equal to L upon the velocity, and this particular velocity is nothing but, once again, it is Vx. So that Vx multiplied by this Vx, this will actually be given as y is equal to d into E upon m into L divided by Vx square. We need to simplify this expression still further. Starting off with the expression y is equal to d into E upon m into L upon Vx square. So we have to find out the expression for Vx square. In order to find out the expression for Vx square, we have to be careful. We actually wish to find out what is the voltage through which the electron has been accelerated prior to entering the electric field. And therefore that will be equal to half of m into V square is actually equal to half of mv square, which is actually equal to Vx square, is equal to E into V, an expression which you already derived. We'll put it as Va, which is the voltage applied, and therefore your Vx is equal to square root of E into Va divided by, there will be a factor 2 over here, and this will be divided by m. I now substitute this in this particular expression over here. Let us say that we are calling this as 1, and let us say this is calling this as 2, and therefore your y will be equal to d into E upon m into L upon Vx square. So that is going to be equal to 2E upon m into Va, and after cancellation of the terms, this will be equal to y is equal to d upon 2 into E into L upon V into A. The electric field can also be written as your E is equal to V upon D. In order to understand the difference between this voltage and this voltage, let us first of all refer to the original figure for some time. The original figure, and we have the voltage that is applied between these plates. So capital V is the voltage that is being applied between these plates, and VA is the voltage that is being applied to the electron prior to its entry into this electric field. So one has to be very careful to understand the difference between these voltage and the voltage applied, which is VA. Continuing further with our explanation, your displacement y, which you will see on the screen, is equal to y is equal to d upon 2 into V, I will express this, into L upon V into A. And this expression gives you the deflection of the point. This means the point that is created by the electron impinging on the screen, the deflection due to the electron, or the point that is made by the electron, is equal to d by 2, wherein d is the distance between the plate and the screen, V is the voltage that is being applied between the plates, L is the length of the plates, and VA is the applied voltage to the electron so that it gets a velocity V0 in the x direction. So we now want the angular displacement. So the angular displacement tan of theta is equal to Vy upon Vx. So your theta will actually be equal to tan inverse of Vy upon Vx. So this is going to be equal to tan inverse of your Vy is going to be equal to EE upon M into T divided by Vx, and this is going to be equal to tan inverse of EE upon M into your T is going to be equal to distance upon the velocity. So the distance is going to be equal to either L upon your Vx multiplied by your Vx, and therefore the final answer will be equal to, writing it in a more general form, tan inverse of EE upon M into the distance that is traversed, which can also be x, divided by Vx square. So this gives you an expression for the angular displacement of the electron in a electric field. Sincere thanks, students, for watching this particular video. Stay tuned to Ekeeda and do subscribe to Ekeeda. Thanks a lot.